back. Next, we're going to prove theorem 3.1, which gives us another fact about this determinant function. And we're also going to look at a quick lemma and do a few examples of like how to actually calculate determinants using all of these rules here. So let's see here. Like this is AI started in column I and A sub j started in column j. But to prove this, to prove that when you swap them, that makes the determinant the opposite, we're just going to start with this thing on the left, and we are going to do a column multiplication. We are going to replace column I with the sum of itself and column j. And we know that doesn't change the determinant. So this is still in column I. And then what we can do, now that this AJ is here, we're going to like cancel out the AJ column from the other one so that it just has like an AI in that column. So we're going to replace column J now with the sum of itself and -1 times this other column. And likewise, that's still a column multiplication. That doesn't change the determinant. And we can just cancel out the AJ now, and we're just left with -AI here. Okay, now we can add this to column I to cancel out this AI, and the J and the I will essentially be swapped. Okay, so here's what we have. They have swapped places. It's just that the problem is we still have this negative thing here. But we can deal with that using the linearity by scaling rule. We can say that k is -1 and take it out. Just multiply the whole determinant by that. And everything else will be the same. And all these other ones are all equal because of preservation under column multiplication. All right, so that's that. We actually saw an example of this earlier. The determinant of this first thing here, where the columns were -2 E1 and E2, I said was -2. But if you write them in a different order, it turns out that makes the determinant positive. But we didn't really prove that yet. But it does have to do with just using column multiplication and linearity. You can move everything around that way. Let's look at lemma 3.2. If A is a square matrix with 0 in a column, then the determinant of A is 0. Now, this is intuitive. It's the way it should work if we're thinking of a determinant representing signed volume or area. Like if 0 is one of the vectors, then that's like a direction that the parallelepiped thing has no thickness. And if it has 0 thickness in one direction, the whole thing is like flat in a way, and so the signed volume is 0. The proof is really quick because we can just use linearity by scaling. Like here, 0 is the same thing as 0 times 0, and you can just factor out that 0 using the scaling linearity rule. And 0 times any real number is just 0. So yeah, that's another way that these rules we defined before help make it so the determinant lines up with our concept of area. Now, we're going to talk a lot about diagonal matrices and triangular matrices. This is closely related to echelon form, but there's also going to be lower triangular matrices that are a little different. So anyways, let's read what this says. The main diagonal of a matrix is all the entries of the form A sub II, where the row number is equal to the column number. So we've already been talking about that. The main diagonal is where all the ones live on the identity matrix. So a diagonal matrix is a square matrix where all the entries not on the main diagonal are 0. So everything else over here would have to be 0 for it to be diagonal. An upper triangular matrix is a square matrix where all the entries below the main diagonal are 0. We say upper triangular because the upper triangle is where all the non-zero stuff is. At least everything below is 0. So that's like the stuff you ignore in an upper triangular matrix. In a lower triangular matrix, it's the other way around. Now, a triangular matrix is either upper or lower triangular. So, for example, here is an upper triangular matrix. All the non-zero stuff is on the top part, on the main diagonal or above. So we can use the definition of a determinant function to say what the determinant of this has to be. So if a function satisfies the linearity rules, preservation under column multi-placement, and the first one, the normality rule, then we can just calculate what the determinant of A has to be. So the first thing is we are going to do column multi-placements to clear away this 2 and 3. So let's call columns column 1, column 2, and column 3, just so we can label these things the same way we do it with row operations. So first, the determinant of A using column multi-placements is going to be equal to the determinant of the matrix, where the new column 2 is going to be the result of doing -2 times column 1 plus column 2. So that will give you -2 plus 2 here, which is 0. -2 times 0 plus 4, and -2 times 0 plus 0. And in the same step, let's also do -3 times column 1 plus column 3 to replace column 3 here. Get rid of that 3. Like so. Now we can cancel out this 5 here by doing another column multi-placement using column 2 here. So we can do -5/4 times column 2 plus column 3 to replace column 3. So this will be 0 minus 0, -5 plus 5, and -0 plus 6. Now we see it was pretty quick to turn this triangular matrix into a diagonal matrix without changing its determinant at all. And maybe you can see why you could always kind of do that, as long as you have like non-zero entries here and here to make that work. Anyways, now we want to get this to be the determinant of the identity matrix, which we know is equal to 1. That's the normality condition. And to do that, we can scale column 2 by 1/4. Essentially take the 4 out. So these are the same thing by the linearity. We can think of, we kind of, we're writing it backwards because we started with the result of this being scaled. But if you scale this 0, 1, 0 column, you get the 0, 4, 0 column. And the resulting determinant is 4 times this determinant. So yeah, that works. And we're going to do the same thing here with the 6. And the result now is just going to be 4 times 6 times 1. That's the normality condition. So yeah, this comes out to be 24. Let's do a couple other examples. Let's look at example 2 here. Now, it says, is this triangular? Well, it looks like a triangle here. Yeah, but the problem is that this is not the main diagonal. The main diagonal is always from like row 1, column 1 to row 2, column 2. So unfortunately, it is not triangular. Well, we'll see if that matters. But just to point out, the triangle has to be either that way or this way. And because this one is not 0 and this one is not 0, it's not triangular. But we could maybe turn it into a triangular matrix. What would happen if we swapped these two columns? Well, let's see. Now, this is maybe not the same thing as the determinant of A because we swapped the two columns, but it is triangular. This is lower triangular because everything above the main diagonal is 0. Okay. Now, what is the relationship between the determinant of this thing and the determinant of A? Well, we can use the antisymmetry theorem here, which says that if you swap two columns, the determinant becomes the opposite sign. Now, let's calculate the determinant of this. We're going to try to turn this into the identity matrix using column operations. Now, to do that, we need to get rid of this -3. But what we can do is replace this first column with the sum of 3 times the second column and the first column. And that does not change the determinant. 1 plus 3 times 0, -3 plus 3 times 1, and the second column is unchanged. And this is 1 because of normality, because we have the identity matrix now. So the determinant of A is -1. Okay. Let's look at example 3, getting a little bit bigger and more complicated now. First of all, let's notice that this is triangular. Like everything below the main diagonal here is 0, so all the non-zero stuff is in the upper triangular part. Let's also notice that in the main diagonal there's a 0. That is actually going to be significant because that suggests that we could use these like pivot positions. I mean, it's not exactly in row echelon form, but we could use this 3 and 2 to do linear combinations of these two columns to make that -6 and 4 go away. And then that's going to be a matrix that has a 0 in one of its columns, and that determinant should be 0. And maybe that agrees with your intuition that, like, if the third vector is in the span of the first two, then it's like the four-dimensional hyperparallelepiped doesn't really point in four independent directions, so it might have four-dimensional volume 0. So yeah, the determinant is going to turn out to be 0. Let's go through the steps to see how it actually works. We're going to do some column multata placements. Let's start by clearing away this 4 here by doing -2 times column 2 plus column 3 to replace column 3. -10. -2 times 2 plus 4 is 0. 2 times 0 plus 0 is 0. Column 4 is unchanged. Now we can do 10 thirds times column 1 plus column 3 to replace column 3. And again, these do not change the determinant. And this is 0 using the lemma that we just looked at. That if you have 0 in a column, the determinant is 0. It was lemma 3.2. And so this is sort of a justification for lemma 3.3 here, that if A is triangular with a 0 entry in the main diagonal, then the determinant of it is 0. And that also means that the volume should be 0 because it's like that linear combination of the other columns doesn't add any extra thickness to it. It's like another vector without any more volume means there's like a dimension in R4 in this case that this shape has 0 thickness. And so the volume is 0. And we've also kind of justified theorem 3.4, that determinants of triangular matrices are the product of the entries on the main diagonal. We saw that with this one, like if there's a 0 here, then, and it's a triangular matrix, the product of the entries is 0, so that works. It doesn't apply to this one, because example 2, because it's not triangular. But it does apply to this one. Here we saw how we could turn this into the identity matrix using column multata placements here and here without changing it. And then once you do that, you can take out the scalars 4 and 6. And you end up getting 4 times 6 times 1. So the product of these 1 times 4 times 6 gives you that 24. So that's an argument for that without an actual proof, but hopefully you get the gist of it. In the next video, we'll look at example 4, but we should probably take a little break, have a drink of water, and I will see you in a bit.